Welcome to another exercise for the workbook statistics. This time I'm going to focus on Spearman's rank correlation coefficient. Our exercise here is the work ethics and the behavior of a sample of pupils from a boarding school is rated on the following scale. And we have the scale with a rating with 5 stars from very good to 1 star of very bad. And additionally, we have data for the 5 students, as we said before, for work and for behavior. If we look closely to this data set, we see that each of our ratings is present only once. And we can see, well, this is information given not in direct quantitative form. So when we are asked to calculate or use a suitable bivariate measure to quantify the strength and the direction of the relation, we need to turn to Spearman's rank correlation coefficient because we do not yet have the numbers we require, for example, for something like Pearson correlation. Well, how to proceed with this? Well, first we need to turn these evaluations into numbers. That's actually the first step we're going to do. We translate our data set into ranks. So we're going to take our data set as is, and then apply the following ranking scheme. The best evaluation is rank 5. The worst evaluation is rank 1. So if we copy the table and then fill in here the corresponding ranks, we get for the first one 4 stars was the second best, was the best, so forth. So we can directly see at this point, we can simply copy the number of stars each of them is assigned. So in the next one we get 5, 1, 3 and 2. Then for behavior it looks similar. We get 3, 4, 1, 5 and 2. Of course, just the number of stars. Then we already have everything we need. So we could use this table and simply start and apply Pearson's correlation coefficient on this data set. That's a solution which always works. However, if we have a situation like this, where we do not have so-called ties, meaning where each rank is assigned only once, then we could also use a shortened version for the measure. Well, I'm going to present to you both versions. Let's start with the more general version, which always works. For this, I'm going to copy the table as is, and I'm going to add 3 additional rows and 2 columns. Well, let's start with the rows. As I said, I'm going to calculate Pearson's correlation coefficient. I need first to square all the results in the x row. Here it's not x, but rank of x. So I'm going to get the squares of rank of x. So 4 squared, 5 squared, 1 squared, 3 squared, and 2 squared. Then I'm going to do exactly the same thing for the rank of y. So I have 3 squared, 4 squared, 1 squared, 5 squared, and 2 squared. And finally, I'm going to multiply rank of x and rank of y. So I have 4 times 3, 5 times 4, 1 times 1, 3 times 5, and 2 times 2. These here are just intermediate steps. So I'm not necessarily going to need them, but if I'm going to add one additional column where I sum up all the values, getting these results here, what I'm actually need is also not this column, but the next one where I'm going to use the sums to calculate averages by simply dividing those sums by the 5 observations. So 15 by 5, 15 by 5, 55 by 5, and 52 by 5. Those 5 values are actually the ones I really need. Not the only ones I need. So you could skip the column for the sums. You could skip these parts here if you just do this on your own by hand. But you will be needed to actually get those 5 values back here. Because the formula for this is simply as follows. It's just the Pearson formula, and we replace x by rx and y by ry. Well, here we have the average of rx times ry, that's a 10.4. Then we have minus the average of rank of X, that's the 3 here, times the average of rank of Y, that's the 3 here. And we divide this first off by square root of the average of rank of X squared, that's this 11 here, minus the average of rank of X to the power of 2. And we do the same thing for Y. So first off, rank of Y squared is this 11, minus rank of Y, that's this 3 squared. And we plug in all these values, giving us these results, and a final value of 0.7. This tells us two things. First off, it's a positive relation, meaning if we have a student who has higher or better rating in work ethics, and we can assume he also will show better behavior. On the other hand, if one student shows bad work ethics, he usually will behave worse. That makes sense. However, this could also work the other way around, because rank correlation, like correlation in general, doesn't tell us anything about the causal relationship. So what actually impacts what? It's just a relation between those two. Well, that's on the direction, so it's a positive relation. And, well, it's 0.7, so it's larger than 0.5, because we have 3 thresholds regarding the strength. Spearman's rank correlation lies always between -1 and +1. 0 being there's no relation, -1 or +1, there's a perfect perfect relation. Well, what does 0.7 mean? Well, we can make 3 thresholds. The first one at 0.1, then 0.3, then 0.5. Below 0.1, there's no relation at all. Between 0.1 and 0.3, there's a weak relation. Between 0.3 and 0.5, it's a medium-sized relation. And larger than 0.5, it's a strong relation. Well, that's larger than 5 or 0.5. So it's a strong positive relation we get here. Well, that was the classical version, the classical alternative, which always works, even if we were to have ties. Now let's turn to the alternative 2, which only works if we have a situation like this here, where in each case we have each rank assigned only once. So that's alternative 2. So we're using the same table, but we're going to add only one additional row. And that's where we go with the difference between those two, and that's exactly the squared difference. So it's 4 minus 3 squared, 5 minus 1 squared, 1 minus 1 squared, 3 minus 5 squared, and 2 minus 2 squared, giving us these results. And then we're going to get our row sums or row totals. Actually, we do not need those two up here, the 15 and the 15. I'm just interested in the 6th down here. That's actually the only value I require, and the fact that I have 5 observations. Because the formula here reads as follows. That's 1 minus 6 times, the 6 is always given, it's always 6, times, then we have the sum of the squared differences. That's actually this 6 here. So this whole part here, that's this value here. And then we divide by n times n squared minus 1. So here we have 5, so 5 times 25 minus 1. So in total we get this intermediate result, and then 1 minus 36 divided by 120, or if we shorten this, 0.7 as in the example before. That's the result in all cases where we have no ties. In those situations, both alternatives provide the same results. In a situation where we might have ties, so where one rank is assigned more than once, or at least one rank is assigned more than once, those two alternatives would give us different results, or in other words, this second alternative would be off. The more ties we have, the more off from the real result it would actually be. So it's simplified version, but the simplified version is always slightly off if ties as such exist in the dataset. Well, that's then it. I hope you enjoyed it, and I say goodbye and see you next time.